This question states, if we have the following configuration for a beam, what is the displacement at the middle of the beam? And the first question we might ask ourselves, in addition to the question that's being asked of us, is whether or not the system is indeterminate. And one simple way to determine whether a system is indeterminate or determinate is to think about the possibility of being able to remove boundary conditions or constraints that would allow the system to still be in static equilibrium. So, for example, this system with the right wall removed and the force or the distributed force applied would still be a determinate system, or would still be statically stable or determinate, right? It's not going to do something like flop around. But if I were to do something like this with the beam, and I removed an additional constraint, changing the wall to a pin, of course, this is just going to flop around like that. So we see that the beam with the walls on each end um, is going to be statically indeterminate to the second degree. Why? Because I could have also, this would be statically determinate to the first degree, whoops, where I just have a roller, right, on that side, but that doesn't have the ability to constrain the moment, which the wall does on the right side. Okay, so this would be first degree, or 1 degree, or single degree of indeterminacy, and this is second degree of indeterminacy. And my handwriting diagonal like this is quite messy. Well, let's go ahead and now start approaching the problem at hand. And indeterminate, determinant, whether you're using integral differential methods, however you're approaching a, a problem that requires statics or equilibrium, geometric compatibility, and constituent relationships, we are going to want to start with looking at external equilibrium. So we could try, maybe we will try here to make our familiar friends the three pillars of approaching mechanics problems. For a long time now, maybe not a long time, but for a little while, we've been mostly focusing on problems that are statically determinate, and so we've only needed to use equilibrium. But now we're getting into these problems again where, well, it's indeterminate, so we have no choice but to keep track of the constituent relationships, because the constituent relationships allow us to solve problems that statics cannot, right? Indeterminate problem is one in which we have more unknowns than we have equations, and that will play out in just a minute as well. So we'll try to keep these kind of three pillars, and maybe geometric compatibility will be quite limited, but we'll go ahead and we have our constitutive relationships here as well. So we'll just try to divide it up into those three categories. Well, for equilibrium, let's first do external analysis, external equilibrium. So I'll draw it out as just a beam with some distributed, that was maybe a bunch of arrows, load on it like this, and this has quantity W naught. And I'm going to already think about how symmetry tells me some things about the problem. It tells me that the load the reaction load on the left, which I'll call R, and the reaction load on the right, which I'll also call R, they're the same. Okay, there's nothing happening across here where I would get a different R on the left than a different R on the right, and also we can say that the M sub R, we'll call it, on both the left and the right, externally now acting on this system, are going to be the same as well. So we can put MR on both sides. And so when we look at the equilibrium in the forces, okay, we could say that we have R plus R minus W naught L equals 0. So therefore R is going to be W naught L over 2. So that's kind of nice. And we can also say that we have the sum of the moments, not a double sum, and we'll say at the left is equal to 0. And what we have here would be that the MR on the left is positive. The equivalent, and I kind of jumped over this, right? That the equivalent, we can kind of cross this whole thing out with an eraser and say that at least when we're doing external equilibrium, I really want it, there we go. Okay, we can write that this is an effective force acting at the middle, and it's acting L over 2 from the left side and L over 2 from the right side. It's acting in the middle, right? So we have MR, that's from the left side, and we have this minus MR, and we have this minus W naught L times L over 2 as well. So this is going to be minus W naught L, and then it's acting a distance L over 2 away. And we have minus MR, because it's going into the board, is equal to 0. Okay, so we can look at this equation and then get super perplexed. Why am I super perplexed? Well, missing something. What am I missing? I'm missing the R. Okay, so I need to say this is going to be plus R L, okay, is equal to 0. And the issue we find now is that the MRs cancel out, okay? And we just get another expression which states that R is equal to W naught L over 2. No new information, and we still have this unknown MR. Okay, so this manifests that using equilibrium alone is not going to be sufficient to solve even for the bending moments across this beam. We're going to need to use constitutive relationships to be able to solve this problem. Well, what is a constitutive relationship that we can use? We can use EI times the second derivative of the displacement across the beam with respect to x is equal to m. Okay. Now, in order to kind of use this m is not this mr, but this is the internal m. So we need to create another free body diagram, and let's go ahead and do that. So this is going to be the internal equilibrium, which will employ method of slices. And in many respects, this problem is kind of a nice review of many of the things that we've talked about this semester in mechanics and materials and in statics, quite frankly. So here we will say, I'm going to take a slice, won't it be nice? And I'm going to have my reaction force R. I'm going to have my MR. And remember that those are external, the moment and the force, and so it doesn't matter too much what we call as direction, but I've kind of chosen logical ones. That said, for the internals, the internal shear force and the internal bending moment, it very much does matter what I use as my internal, and I'm still going to have this external distributed force acting on the system. Okay. Now, you could say, well, you really should use integral differential equations because you're going to be doing them for the moments, but I don't necessarily have to do that. I can kind of think a little bit about um, what about just using equilibrium here to work on this problem. Okay, so we can say that in this case, and so we have the W naught here. The equilibrium for the forces, okay, we'll have us with, and this is going to be a parameter x, and there's no additional load. If I go all the way back up here, there's no additional load or concentrated force coupled moment or change in the distributed force as we go along this beam. So it's fine to just stick with an x parameter across it, right? I don't need to do like an x1 and x2 or nothing like that. Um, so uh, so let's do the equilibrium here. We have R, V, and W naught. So we're going to have R upward. We'll have W naught X downward, and we'll have also our V downward, and that will be equal to 0. Okay, and yes, we can put in what R is equal to. We already know that it's W naught L over 2, but we'll just leave it as it is, and we can write out that the shear force is going to be R minus W naught X. For the moment, and maybe it's a little confusing, that's M and that's M, or we could just say the moments, if we want, equal to 0. And let's do, I don't know, let's do at the right side. Okay. So when we have that, we can write out that we have our MR is a positive moment on the left side. We have an RX, which is going to be minus, or XR, if you will. We can say that V is not going to be contributing anything. We can say that we have a positive W naught X acting at X over 2, right? That's acting effectively there. Yeah. So I'm just going to take that out. But and then we have our positive moment internal, okay? And so if we want to solve for M internal, we can write out that we're going to have minus MR plus RX and minus W naught X squared over 2. Okay, yep, that's done correctly. So now I have an expression that I can, if we go all the way back, okay, over here, okay, we have an expression that we can use. So that's M and that's M right here. Now, we don't know what MR is, And maybe I should not have r sub x. No, it's just r times x. But we do know what r is. And so let's just go ahead and do a substitution. This is going to be minus mr. Okay, r is w naught l over 2, so we can say that's going to be w naught l over 2 times x. And we have minus w naught x squared over 2. Just like that. So we can go ahead and we can integrate there. So we have this EI, well, let's change colors. We have now our EI, first derivative of displacement with respect to x, and it's going to be and so it's okay. We know that we don't know what mr is, but we do know it's going to be a constant. Okay, so that means that we can write minus mrx plus, now we have squared, so this is going to be w naught l over 4 x squared, and this is going to be to the third, so it's going to 1 okay, so minus 1 w naught x cubed over 6. Plus, since it's an indefinite integral, plus c1. Okay, just like that. So there's a little c1 there that you can kind of see. Now, maybe it's a good idea to think about boundary conditions, and let's lump the boundary conditions in this category of geometric compatibility. Why don't we look at the problem again and see what's happening at the boundaries? We know that little v of 0 is going to be 0, which is also going to be little v of L. We also know that the angle at 0, so that's dv dx, all right, at 0 is going to be equal to 0 because this is a wall, and so that means that at the wall, the beam is going to come straight out. It's not going to, it can't slope, and that's equal to the theta at L as well. So this dv dx is equal to theta. So maybe we can take advantage of this boundary condition, right? We have the theta of 0 is equal to 0. Well, that would be nice, right? If I plug in 0 here, I see that I have zeros, right? So using this, so using theta of 0 equals 0, we get that c1 is also equal to 0. And now let's perform another integration. Let's look at, maybe we'll change it to that color. Let's do EIO? No. EI times little v is equal to, all right, so now we have minus mr over 2x squared, and we're going to get to plus 1 naught L over 12x cubed, and then we'll get to minus W naught x to the 4th over 24, and we'll call it plus C2. Well, what boundary condition could we use here? Well, let's see. We can go once again say using something that we have here, the v of 0 equal to 0. All right, we can see, oh, that means that C2 is also going to be equal to 0. So using v of 0 equal to 0, we can say that C2 is also equal to 0. Okay. Well, this is quite nice. We're still though, right? So now I've got an expression. So maybe I can bring it down. It's nice here that EI times the displacement is equal to minus mr over 2 x squared plus w naught L over 12 x cubed minus w naught x to the fourth over 24. Okay, this is very nice. But I don't know MR. I still don't know MR. Okay, but I have used more information than what I had in over here when I just did equilibrium, when I was using equilibrium. So maybe there's another boundary condition that can help us figure out what MR is going to be. Well, of course, we can say, we can use that displacement at L is equal to 0. So we can say the displacement at L is also equal to 0. And that one's maybe not as simple as a, C2 equals 0 or C1 equals 0, but we can plug in the numbers and we can solve for the MR. So what we get is, well, let's solve M minus M sub R over 2 times L squared plus, now we have our W naught, it's just L, so we're going to get W naught L to the fourth over 12 minus W naught L to the fourth over 24, and this is going to be equal to 0. Well, we got this one unknown. Everything else here is a known parameter, so we can write out that MR, okay, is going to be equal to, okay, so this is 1/12 minus 1/24. That's going to give us 1/24, and it was over 2, so it's times 2, and we got rid of an L squared, so it's going to be 2 times 1 over 24, and it was going to be, and this was negative, so this is now going to be negative, and no, it's actually going to be, sorry, it's going to be positive because it's got negative, negative, right? So this is, yeah, this quantity is going to be 1 over 24, but then there's a negative here, yes. So this is going to be W naught L squared. And so that means that we get W naught L squared over 12 for MR. And that's taking advantage of our three pillars: the equilibrium, the geometric compatibility, and the consistent relationships. And so we can finally write out the expression for displacement across, and maybe I'll say, okay, the little v as a function of x is equal to 1 over EI, and we have our MR over 12. So, this is MR over 12, but it's over 2 here, so it's going to be minus. And why don't we bring out a W naught L squared maybe? So that would be kind of nice. So let's do that. So we can do W naught L squared as well there. So this is going to be x squared over, and it's actually a little bit not great because we have this L, so we'll just leave it there. Yeah, we have an L, da, 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 da. So, changing things up a little bit. So W naught over EI, this will give us a minus L squared x squared over 12. Now, maybe it would be nice to bring a 12 out. Does that sound good? Yes, or maybe a 24. Sure, we can bring a 24 out. So let's do that. 24. So I'm not going to bring the number to negative. So W naught 24 EI. Appreciate your patience. And this is going to be L squared x squared, and it's going to be minus. You just see that we've substituted that in. We will have a plus 2lx cubed. So that's going to give us a length to the fourth. You see that trend here. And this will give us minus w naught, whoops, no w naught because I already put it out there, x to the fourth, like that. And so that is our resulting expression for this, this problem. Now, did it ask us for any information? Say, okay, what is the displacement at the middle of the beam? All right, so we got, in order to figure out the displacement at the middle of the beam, right? So displacement at middle of beam would be v, little v of L over 2, right? At x equals L over 2. So here we go. V of L over 2 is equal to W naught over 24 EI. And now we have our minus L squared times L squared over 4. We have plus 2 L times L cubed over 8. And we have our minus L to the fourth over 16. Okay. And what do we see? We see, well, this is 2 times 2 over 2 times 1/8. So and so these two are going to cancel out, and we're just left with minus L to the fourth over 16. So we're going to have and that's because I don't actually know what 24 times 16 is. Okay, and that's the final answer. All right, so thank you for watching, and I hope this example has been useful to you. We have been able to harken back to some of our earlier principles of equilibrium, geometric compatibility, and constituent relationships to solve for the elastic curve across this indeterminate beam.